Okay. Uh, Good evening, students. So, can you tell me, please drop me a message whether you can hear me or not. Please drop me a message whether you can hear me or not. Please drop me a message in the YouTube live chat area. Okay. Please drop your names or drop me a message whether you can hear me or not. Okay. Right. So, what about others? Students, those who join the class from the number 0 class, like from the students, those who from the physical class, please drop your names so I can identify you guys. Right? Okay. I think you can hear me, and let's start the lesson today. Okay? Right. Others, please drop your names. In our last class, we studied about the echo that's finished, and we studied about the reflection. Okay, we studied about the reflection and the refraction. I think that the refraction part also finished. Okay, right, the refraction part also finished. Today we are going to study about the diffraction of waves. Okay, so today we are going to study about the diffractions of waves. Right, okay students, so let's move to the class now. So first of all, you should know what is diffraction. Okay, right. So I think in chemistry, did you all heard about the double slit experiment? Okay, right. Did you all heard about the experiment, double slit experiment? Right. Okay. So I think most of the students heard about the experiment. I'll come to that later. First of all, we'll go to the diffraction of waves. Okay, right. Look at the definition under the diffraction of waves. I can open the tute here. Okay, right. So that's easy. Okay, right. So we didn't do that part. I'll explain you. Okay, this one, yeah, I got it. Okay, right. So we studied about the echo and the, yeah, we didn't do this one. I'll explain you this one. Okay, like the diffraction. Okay, diffraction of waves. Okay, right. So let's start the lesson now. So diffraction means, look at this one. There is a, let's say we'll come from the light's diffraction. Okay, diffraction of light. Diffraction of light. Okay, right. So first of all, let's study this part. So diffraction of light here, okay, right. So this is the water surface, and when a light beam is coming from the air, what will happen here is, guys, okay, when a light beam is coming from the air, what will happen is this light beam's path will it will change, right? Something like this. Okay, let's say this is water. Let's say this is water, and this is air. Okay, right. This happened, we studied in our last class, this happened due to the difference in velocities in different mediums. So you should know that in air, that is a different speed for the light. It is like, what's the value? 3 into 10 to the 8 ms minus 1. But in water, the light speed is very low, right? So there is a difference between the mediums. So that's why this diffraction is happening. So what's the reason for the diffraction? The reason for the diffraction here is the difference between the speed of light between the different mediums. Okay, right. So this is the reason. So we should know that the Snell's law we already studied in the O levels as well. That's very simple. Let's say this is the, let's say this is I, this angle is I, and this one is R. This one is R. Okay, right. We should know that refractive index. We already studied about the refractive index. Let's say for the water, the refractive index here is N, and the if it is an air or a space, this refractive index here is, guys, 1. So this refractive index that is equal to, or I can say like this. This is Snell's law. I can say like this. Let's say, let's mark it like this. Let's mark it like this. This medium's refractive index is 1, N1. This medium's refractive index here is N2. I'm marking like this. So what we can say here is, guys, the relationship between the N1, N2, I and R here is like this. I can give like this. N1 sine I is equal to N2 sine R. N2 sine R. So this is the relationship between the refractive indexes of the mediums and the I and the R values. Okay, right. In your exercise book, that is clearly mentioned. Okay, that is clearly mentioned here. So showing the validation of Snell's law theoretically. So we don't need this kind of validations. We'll study these validations in light part. There is a detailed subject is there. We will study them later. Here you should know about how it's happening. This is the only thing you should know here. Okay, right. This is very important here, guys. And also you should know about this thing as well. Let's say this is the frequency. The frequency of the light here is F. We know that this frequency is dependent in the color. Let's say if I take a red color that is having a different frequency. Blue color that is having a different frequency. Likewise, when the color changes, the frequency also changes. When the color changes, the frequency also changes. You should remember that one. Okay, right. So in this light beam or light ray, the frequency is constant here. It won't change. If it is F naught, the refractive light also F naught here. Okay, right. So look at this one. So this is not like diffraction, refraction, right? Refraction. We are studying about the refraction here. Okay, right. So we should know that, let's say the speed in this area, in the air, let's say it is like V1, and in the water, the speed of the light here is V2. I'm taking like this. So what we can do here is we can apply the V is equal to F lambda equation for this ray and this ray. We can use, right? When I'm using here, V is equal to F lambda, V is equal to F lambda. The velocity here is V1 is equal to, the frequency is F naught into, let's say The wavelength here is lambda 1. So from this equation, so here when I apply the V is equal to F lambda equation for this ray, how we can write here? V2 is equal to F naught. V2 is equal to velocity of the light. It will be changed because of the medium is changing. That's the reason. So V2 is equal to F naught lambda 2. F naught lambda 2. Okay, right. So when the refraction is happening, you should remember that frequency is constant. Its frequency is constant. So from this one, we can say that while a refraction is happening, V proportional to lambda. Okay, right. When the velocity increases, the lambda increases. When the velocity decreases, the lambda decreases. Okay, right. So in this case, which is the highest velocity? We already know that in the air or the space, the speed of the light is 3 into 10 to the power 8 ms minus 1. That is the maximum speed of the light. Okay, that is the maximum. It can't be above from that value. Okay, right. It can't be exceed. Okay, right. So this is the maximum speed. We already know this one. So I can say that V1 is greater than V2. So V1 is the greatest one and the V2 is the lowest one here. So what will happen here is, guys, when the V increases, lambda increases. When the V decreases, the lambda decreases, because V proportional to lambda here. Okay, so what will happen here is, guys, look at this one. This ray that is having long lambda and this one is having low lambda. This is having a like the highest lambda. The lambda is high here, the lambda is low here. Lambda means the wavelength. So look at this wavelength. We already studied about the wavelength. This is highest value, and these are smallest value. Okay, right. So this is how it will be looks like. Let's say this is for a light ray, light ray. Okay, so let's say there is a refraction is happening. There is a refraction is happening in a water surface. Okay, right, in a water surface. Right. What I'm going to do here is we can experience this one using the ripple tank. I'm taking that for an example. I'm taking a ripple tank here. Okay, right. While I'm taking the ripple tank, I'm creating. So this is how the ripple tank looks like. This is the cross section of the ripple tank. Okay, cross section of the ripple tank, and this is how the water fills inside the ripple tank here. Okay, right. In the ripple tank, you already know that the height of the water here is from the bottom is like, let's say it is h. Okay, right. So how can we create two different mediums inside the ripple tank? This is the next question. How can we create two different medium inside a ripple tank? That's very simple. You can change the height here, guys. So what I'm going to do here is I'm going to change the height. That means I'm placing a small glass piece inside the ripple tank like this. So here, guys, so this is water now. So this is water. This is water now. These are the water. This is water. This is also water. This is also water. Okay, right. So what is happening here? I'm changing the height of this water. In this side, left side, the height is increasing. Here, this is high and this height is low, because the below in this area I covered with the glass. Okay, I covered with the glass here. So how it is possible that how I know that there are two different mediums? Right, look at this one. Different medium means in that two different mediums, the velocity will be changed. Definitely there are two different velocity areas. So actually what I want to do here is I need to create two different areas with different velocities. Okay, two different areas with two different velocities. So look at this one. While you are looking at this one here, this is air, this is water. Water, there will be a different velocity. In the air, the light's velocity is different. In the water, the light's speed is different. So there is a difference between the speed in these two mediums. This one also, guys, like that. Okay, this one also like that. Look at this one. So how we created this one? By changing the height of the water. How it will be possible? I will explain you. Right. There is a theory behind this one. There is a theory behind this one. Let's say there is some water inside a tank, something like this. Let's say this is H. This is H. So let's assume that we are creating a wave here. Let's assume that we are creating a wave on the surface, on the water surface. We are creating a wave on the water surface. This wave's velocity is known by, this wave's velocity is known by V is equal to root GH equation. Root GH equation. What is this? The wave's velocity is equal to root of gravitational acceleration into water height. Into water height. Look at this one. What is the height here? The height here is h. So V is equal to root of GH. Look at this one. In this case, guys, this water height here is h1. Water height here is h2. H1 and H2 here. So, what is the velocity of this water surface? We know that we can say V1 is equal to root of G is constant, no, GH1. For this water surface, we can say V2 is equal to root of GH2, root of GH2. So, I created two different mediums here. Okay, I created two different mediums here. Left side different medium, right side different medium. Which is having higher speed of the wave? This one, because the height is higher in this one. This is lowest height. So this is having higher speed and this is having the lower speed. So we can say that. So we can say that V1 is greater than V2. Okay, right. You should know about these things, guys. So this is how we can create two different medium using ripple tank. Okay, right. So it's very simple. We can create it like this. So we created. It is done. We created. Right. I'm looking this ripple tank in an aerial view. So aerial view means when you are, it is like a bird view. Okay. So aerial view means we are seeing something from the top. Okay. Right. So we can see the aerial view. When we are considering the aerial view, let's say we created two different kind of mediums here. Okay. Right. So look at this one. So this is the medium one, and let's say this is medium one, and this is medium two, right? Okay. So there is a water. There is a parallel wave. Uh, let's say there will be a parallel. Parallel wave fronts are coming from this point. Parallel wave fronts. Okay, right. So the parallel wave fronts are coming from this point. Okay, look at this one. I'm going to draw the parallel wave. So I'm going to draw the parallel wave fronts. So the parallel wave fronts looks like this, no, guys. So these are the parallel wave fronts. Okay, but I'm going to mark this. These are the parallel wave fronts here. So the parallel wave fronts are coming in this side. Okay, right. We already studied about the wave fronts earlier. We studied about the wave fronts earlier. So I'm going to erase this one. Okay, something like this. Okay, like this. So the parallel wave fronts are coming. This is the different medium. What will happen here is, guys, the refraction will happen. What will happen? The refraction will happen here. When the refraction will happen, this is the pathway of the parallel wave fronts. No, what will happen here is, it will refract like this. So this is the path of the wave here. So this will refract like this. So we know the path now. We found the path now. So now what I want to do here is I want to draw the wavefronts. Again, I need to draw the parallel wavefronts. Now this is refracting here in this surface. So what will happen here is what I am going to here is I'm going to draw the lines again like this. So that is clearly given in your uh, tudes. I'm going to draw that one as well. Right, they will be looks like this. The refraction will looks like this. What is the reason? There are two reasons. One is the wavelength. So you already know that the length between two wavefront here is lambda. In the last class, I gave you the note. The distance between two wavefronts here is lambda. Let's say this is lambda 1. The velocity here is v1. This is lambda 1. The velocity here is v1. And let's say here the lambda should be lambda 2 and the velocity here is v2. So what I'm doing here, look at this one. The height of this area, we know that that is h1. So h1 is the greater one. So the velocity also greatest one. So we can say that v1 is greater than v2. If v1 is greater than v2, v is proportional to lambda. No, when the v increases, lambda also increases. So here, what I can say here is lambda 1 is greater than lambda 2 as well. So this is why we are drawing like this. So while the refraction is happening, what will happen? The lambda also changes. So this refraction will happen. This refraction obey the rule of Snell's law, which we earlier studied about here in the lights. Okay, so in the light there is a Snell's law. No? Snell's law. There is a Snell's law. So we know the law here. Regarding to this law, this will happen. Okay, right. So this is how it's going to work, and you don't need the proofs here. Okay, anyhow, you don't need the proofs here. You should know about this one. You should know about this one. I will tell you. Uh, yeah, this will be looks like this. You should know about this one. Like I will mark that one as well. Okay, right. So look at this one here. Let's say the velocity here is v1. The velocity here is v2, guys. v2. The relationship between the refractive index and the angles are here. N sin I is equal to N2 sin R. I can give another relationship also here, guys. Sin I over sin R is equal to V1 over V2. This is the second relationship. This is like a relationship between the angles and the velocities. Angles and the velocities. So this is Snell's rule. Okay, you should remember these two rules here. Okay, right. So we will study deeper about this refraction of light in the light part. That is very simple. So like this is in wave, so you should remember this one. Okay, right. Let's say there is a refraction is happening, right? So I think I gave you all the notes regarding this one. If you need, you can note this down. If you need, you can note this down in your exercise book, this part. Okay, right. I think I gave you. That is not in the note, so you can write this one. Okay, that is not in the note, you can write this one in your exercise book. So the speed of the wave is given by, speed of the surface wave is given by v is equal to root of gh. So write this one in your exercise book. Someone is asking like, is there a relationship between the energy and the amplitude? Yes, like we will study that part later. That part is also in the in this textbook. Okay, I'll explain that part later. I'll explain that part later, guys. Okay, right. So please note this one in your exercise book. Right. Shall we move to the next one? I will complete, right? I will complete. If you all completed, please let me know. Please drop me a message here so I can see. Okay, yeah. I think you all completed the note, so we can move to the next one. We can move to the next one here. Okay, right. So what I'm going to do here is I'm going to move to the diffraction of wave. Okay, I'm going to move to the diffraction of wave here. This is very simple. Very simple one. This is the third one. This is the third characteristics of the wave. This is the third characteristics of the wave. One is reflection. The second one is refraction. The third one is diffraction. Okay, the third one is diffraction. We study about the third one. We are going to study about the third one, diffraction. We are going to study about the diffraction here. Study about the diffraction here. Okay, right. Let's go to the diffraction. Dispersion of waves occur when they pass through a hole or travel passing a barrier is called wave diffraction. Diffraction of water wave could be shown by using a ripple tank. Okay, right. Wave diffraction depends on wavelength of the wave and size of the hole of the barrier. Okay, size of the hole of the barrier. Okay, this is the thing they are given here. Okay, right. Let's go for the theory now. Okay, diffraction is like the spread of the wave. Okay, it is like the spreading. We already know that how the wave will spread. So those patterns are, when I'm saying it in simple terms, it is like that, the spreading. Okay, right. That is the word they given here. Dispersion. Okay, dispersion of wave occurs when they pass through a hole. When a wave is passing through a small hole, how the patterns looks like, how the patterns looks like, that is diffraction. Okay, right. So I will explain you, I can explain you the diffraction here. I can explain you the diffraction here. Okay, right. I can show you the diffraction as well. So diffraction of waves in ripple tank, we can see this one. Look at this one. This is the best one, I think. Okay, look at this one. So this is a ripple tank, guys. Okay, this is a ripple tank. So they are filling the ripple tank with the water now. They are filling the ripple tank with the water now. Look at this one. Okay, right. So they fill with the water. Look at this one. So the ripple tank is here. This is the ripple tank. The bottom part of the ripple tank, that is made of the glass. The bottom part of the ripple tank, that is made out of glass. Okay, so glass means the light rays can go through the glass. Okay, so bottom part, at the ripple tank's bottom part, we can see the shadows. Okay, look at this one. So right, so here what they are doing is using the vibrators, they are creating parallel wavefronts. So using the vibrators, like when we can do like this. So if this is the ripple tank, I can take a parallel rod, something like this, and when I'm moving like this, I can simply create what? Parallel wavefronts here. So I'm creating parallel wavefronts here, right? So these are the parallel wavefronts, right? Look at this one, guys. This is the hole. This is the hole. When the parallel wavefronts are coming through the hole, what will happen here is the wavefronts will diffract. The wave will diffract. That is what happening here. Look at these are parallel waves, but here after the diffraction, the waves looks like circular wavefront. So the parallel wavefront is becoming circular wavefront here. Okay, right. That is not the wave diffraction. Diffraction means like it is the wave is coming in through this hole, the wave is spreading here. Okay, so there are different kinds of spreadings are there. We study that part here. Okay, now look at this one, how these waveforms are coming through the hole. Look at this one. These is the hole now. This is the hole. When the wave is coming, the parallel wave is coming here. Here, what is happening here is, look at this one. Here, what is happening here is the parallel waves are coming from this part. So this is the vibrator. This is the parallel bar. This is the vibrator. So the vibrator is vibrating here. And when the parallel wavefronts are coming through the hole, here guys, the circular wavefront are here. They are coming here. Okay, they are forming. It is forming the circular wavefront. Okay, right. Look at how it's making. Look at this one. This is the hole. So these are the parallel wavefront. This is the vibrator. It is making, and the whatever wave is going like this. Okay, right. So there are lots of examples for the ripple tanks diffractions. So this is also a ripple tank, and this is the we can say that this is the vibrator is there, and this is the bottom part. Look at this one, guys. The ripple tank's bottom part is here. This is the ripple tank, and this is the bottom part. Okay, this is the aerial view. So this is the bottom part. In the bottom parts, we can see that there is a shadow because the ripple tank is something like this. No, there is a box. So we are filling with the water. The bottom part is glass. So when the light is we are applying the light from the top. So when the light rays are coming through the water, so it will go through the glasses, and we can see the pattern at the bottom. That is very simple. Now we are seeing those kind of patterns while raining, right? Okay, so at the bottom part there's a screen. At that screen we can see the reflections. Okay, in the last class I explained you about how the wavefronts are making black and white lines. Okay, because those wave patterns are like convex and the concave lens. Okay, so they are spreading the waves and they are focusing the lights, and spreading the lights and focusing the light. Both are happening in the wave patterns. So that's why the dark and the bright line are forming in this screen. I clearly explain you in the last class. Okay, right. So this is the screen now, so we can see the practical. So this is the setup here. They are creating the. So now look at the view. Look at the view. This is the top part. This is the box. This is the ripple tank. We are filling that one with water. Okay, right. Look at this one. So below the tank, we are seeing this is below. Below the tank, we are seeing the shadows here. Okay, below the tank, we are seeing the shadows here. These are the two bars, and this is the hole. This is the hole. The parallel waves are coming by vibrating this one. By vibrating this one, by vibrating this bar, the parallel waves are coming. The parallel waves are coming here. The parallel waves are coming from that part. From this one, and we can clearly see how the diffraction is happening in this part. Right. Parallel waves are coming. Look at this pattern. Look at this pattern. Look at the diffraction. Now the diffraction is like between these two parts. Like the diffraction is happening here, like this. How the diffraction is happening. Okay, right. This is parallel. So something like you can you can see kind of some reflections here because of that net part. So that is a different thing. So these are parallel lines. Assume that these are parallel lines. Okay. Okay. So this is the refractions happening. So when we make this hole small, the diffraction will increase. You can see that one as well. They are not doing that part here, right? So those are the things we should know. Okay, right. So that's enough, I think. So first of all, we can create barriers in the what? We can create the barriers in the ripple tank and we can make it, right? Okay, so the parallel waves are coming here, guys. I'm marking like this. The parallel waves are coming. The parallel waves are coming like this. I am creating a barrier here. This is the barrier. This is the barrier here. So I'm making a small hole. This is the hole, guys. This is the hole. This is parallel wavefront. Parallel wavefront. Parallel wavefront. So what will happen? The diffraction will happen. The diffraction looks like this. You can draw this like this. So between two lines, between two, like the diffraction will be looks like this. Huh? The diffraction will be looks like this. Okay, the diffraction will be looks like this. This is how it's happening. This is how it's happening. Okay, right. This is known as diffraction. This is known as diffraction. So let's go to the next one. Yeah, the next one. When width of the hole decreases relative to the wavelength of the wave, dispersion of wave diffraction increases. So the diffraction, right. So what they are telling here is when width of the hole decreases, relative to the wavelength of the wave, dispersion of the wave fraction increases. So the dispersion will increase. So the dispersion will increase. I will explain that part here. Look at this one. I will explain that part here. What I'm going to do here is I'm going to make an experiment. This is experiment number one. Experiment number one. In this experiment, I'm making a small hole and a big hole. So here the wavelength of the parallel wavefronts are same. Wavelength of the parallel wavefronts are same here. Wavelength of the parallel wavefronts are same here, guys. Okay, right. So in this experiment also same. This experiment also same wavelengths. There's no difference between these two wavefronts. Okay, right. So what I am saying here is this wavelength also lambda, this wavelength also lambda, this wavelength also lambda. Both are lambda here, but the difference here is the size of the hole. This is the small hole, this is the bigger hole. Okay, what is happening here is when the hole size increases, we are maintaining the lambda constant here. When the hole size increases, the diffraction, the dispersion will, when the hole size increases, dispersion will reduce. The diffraction will reduce like this. For this one, the diffraction happen like this between these 2 points. So the waves are spreading in a very big area. Okay, in a very big area like this. This will spread like this. The wave will spread like this in a very big area. It will spread like in a very big area, guys, in a very big area. But the diffraction is higher here. Okay, it is the big value, like the diffraction is happening here very clearly. We can say the area that is very big here, But in this case, the diffraction looks like this. The diffraction will happen in a very small area like this. So you should remember that. You should remember that when the hole size decreases, the diffraction increases, the dispersion increases. So I can write down a statement here. When the hole size increases, when the hole size increases, when the hole size increases, the diffraction or dispersion will reduce. The dispersion will reduce. Okay, when the hole size increases, the dispersion will reduce. When the hole size reduces, when the hole size reduces, the dispersion will increase. Okay, right. So when the hole size reduces, the spread is high. The spread is high. When the hole size increases, the spread is low. The spread, I am using the word spread here. Spread. Spread. Okay, right. So we can compare the spreads here using this experiment number 1. And also I'm going to move the experiment number 2. Before that one, you can write this one in your exercise book. Write this note in your exercise. If you are having any doubt, you can ask me, guys. If you are having any doubts here, you can ask me. Okay. So if you are having any doubt, please ask me so I can reply you. The lambda is constant, but the spread will increase and reduce due to the hole size. So you should know about the okay, right. Yeah, okay. So shall we move to the next one? Did you all complete it? Please let me know so we can move to the next one, okay? Okay, so are you all done? So after this, please let me please put a message so we can move to the next part. You should know about the spread here, okay? Right. So when the hole size decreases, the spread will increase, and when the hole size increases, the spread will reduce. We can use the word dispersion of wave. Dispersion of wave. Dispersion of wave. Dispersion means spread. Okay, you can say dispersion. Dispersion. Dispersion means spread. Or you can say like it is spreading, right? The spread. We can use this word. Okay. So we can use the similar word for this one, like diffusion as well. Diffusion. Okay, diffusion, dissolution, spreading, spread. So those kind of words are the similar word for the dispersion. Similar word for the dispersion. Okay, right. Shall we move to the next one? Let's move to the next one here, guys. So what will happen here is the next one. What will happen here is when the wavelength decreases while width of the hole remains constant, wave diffraction decreases. Wave diffraction decreases. Look at this one. Look at this one. For like in the experiment 2, in the experiment number 2, in the experiment number 2, look at the experiment number 2. In this case, I'm going to maintain the hole size same. I'm going to maintain the same hole size. I'm going to maintain the same hole size. This is also like constant. This is also constant. I'm maintaining the same hole size. Both are same hole size, okay? Right. Both are same hole size. So what I'm doing here is, guys, the waves are coming. The wavelength is now different. Like I'm sending like the large wavelengths here. Large wavelengths, wavefronts here, okay? Large wavefronts here in this direction, the large parallel waves are coming. The wavelength is high here. The wavelength is bigger, okay? Right. In this case, these are smaller wavelengths. The wavelength is smaller here. Wavelength is smaller here. I'm going to mark this one as well, like let's say this is like lambda 1 and this is lambda 2. Lambda 2. Okay, right. So the lambda 1 is greater than lambda 2. Lambda 2. The whole size are remaining the same. Whole size are remaining the same. So what will happen to the dispersion now? What will happen to the diffraction now? What will happen here is that I clearly mentioned here, for the higher lambda, the spread will increase. The spread will increase. This is the spread. Look at the size of the spread. It is spreading like this amount, not like this. It is spreading like this amount, very big amount. Okay, the spread. So the spread looks like this. So the spread looks like this. So the dispersion looks like this. Dispersion looks like this. For this one, the spread will decrease. When the lambda decreases, the spread will decreases. In this experiment, the hole size is constant. The whole size is constant here. The whole size is constant here. So the spread looks like this. Small spread, small amount of spread. So this is known by, this is known by what? This is like the dispersion. Something we can say like diffraction as well. Diffraction as well. So, or spread. So this is also same. So you can say like dispersion, or diffraction, or we can say the spread, word spread. You can say like this. Okay, so please mark this one in your exercise. So when the lambda, when the wavefronts are constant, when the wavefront, the experiment number 1, when the wavefronts are constant, when the hole size decreases, the dispersion increase. Hole size reduced, when the hole size is small, dispersion will increase. When the hole size is big, dispersion will reduce. Okay, right. So that is like opposite. Okay, right. In this case, when the hole size are remaining the same, when the hole size are remaining the same, if the wavelength increases, the dispersion increase. This is proportional. So when the wavelength increases, the dispersion will increase. When the wavelength reduces, the dispersion will reduce. The dispersion will reduce. That is clearly in the note. And also you can see the image. You can see the image of the dispersions here. How clearly is mentioned here. You can see in this experiment. You can see. Okay, right. So in this here, you should know about these things as well. Okay, right. Please write this down in your exercise book. After completing it, please let me know. You know, guys. We can use the word dispersion, diffraction, or spread to know the diffraction. Okay, these kind of words they will use in the examinations. Okay, so shall we move to the next one? So what about the velocities here? Someone is asking about the velocities here. Yeah. Right. So, okay. it is hard to judge the velocities here. It is really hard to judge the velocities here, because like we need to like this is a different lambda and this is a different lambda, so actually the both velocities are different here. So likewise we can't say that one comparing these two. So don't worry about the velocities here. Please take time to understand the diffraction only in this part. Okay, while doing the questions in diffraction, we'll go to that part later. Okay, right. So you'll study them in you study them later. Right. Okay. So don't worry about the velocities here. Please try to understand the diffractions. Yeah. So you can see the nodes as well. The nodes. So look at this one, like this is the whole size is this whole size. Look at the whole size. In these three experiments, I'm increasing the whole size. I'm reducing the whole size. In these three experiments, I am reducing the whole size here. For this case, like this is the biggest hole. So like this, the berry is like this, the hole is like this is the entire hole. So the hole is something like this, guys. Okay. So in this case, the spread is low. I mean the dispersion is low. When I'm reducing the hole, what is happening here? There will be a certain dispersion. Comparing to this one, the dispersion increased here. Comparing to this one, dispersion increased here because of the hole size. Again, I'm reducing the hole size. So this is happening. Okay, right. So you should know about these things in dispersions. Okay, right. So the next one, we are going to move to the principle of superposition. Okay, principle of superposition. Take out your note. We'll move to the next part. So I already sent you the notes, guys. So if there are any new student here, if there are any new students, you can get the tudes in the next physical class, which is going to happen at number 0. Okay, is there any new students here? So the new students can get the tude from the number 0 when you are coming to the physical class. Okay, right. Okay, right. So what I'm going to do is I'm going to move to the next one, principle of superposition. Okay, right. When two waves are acting in a common medium, resultant displacement of those two waves, resultant wave at any point is equal to the algebraic sum of the displacement created by each wave individually. Accordingly, when taking the shape of the resultant wave formed by overlapping of two waves created by two sources from a certain moment, we have to obtain the algebraic sum of displacement created by each source separately, and shape of the resultant wave should be taken according to that. Principle of superposition could be applied to wave pulses and as well as waves. So we can use to the waves and the waves pulse. So I can give you some examples in superposition. Okay, right. I'll give you some examples in superposition. Yeah. Okay, so look at the note. Instance where principle of superposition of wave is used. First one, to find displacement of wave at a certain moment. The second one, these are the uses. The second one, resultant displacement time graph is obtained by superpositioning the displacement time graph of waves created by two sources which are oscillating harmonically. Right? Okay, guys. So I will explain you what is superposition here. Right. So let's move to the superposition. Wave superposition. Okay, right. So the superposition is like the resultant of the wave pulse. Resultant of the wave or wave pulse. Okay, resultant of waves or wave pulse. Let's say there is a rope is here. Let's consider there is a rope here. This is the rope, okay, guys? This is the rope. In this rope, I'm creating two pulses. In this rope, I'm creating two pulses like this. One pulse is like this. The other pulse is like this. Two pulses. So these two are pulses. Pulse means when I make the rope something like this, I can create a pulse. I can create a pulse. Okay, right. So let's say the amplitude of this pulse here is, let's consider it is A1. Amplitude of this pulse is A1 and amplitude of this pulse is A2. These two pulses are coming opposite. These two pulses are traveling like this. Okay, something like this, opposite. It is traveling in opposite directions. When they are meeting, when the superposition will happen, right? When the superposition is happening, at that moment, the rope will be looks like this. Superposition means the both are meeting. When the both of the waves are meeting, guys, the resultant will be looks like this. Resultant amplitude will be looks like this. Let's say if the amplitude is A, guys, here, if the amplitude is A, we can say that A is equal to, A1 plus A2. So this is the resultant. When the both of the pulses are meeting, the amplitude will be the algebraic sum of these two amplitudes. Okay, right. So this is known as superposition. After the superposition, what will happen? After the superposition, the wave, the pulse, that will move itself in their own direction. So this is coming from this side, this is coming from this side. So this is superposition is happening here. After the superposition, it will move like this. It will move in their own way. Something like this. So this is moving like this is A2, no? So this is moving in this direction. The amplitude is A2 and the A1. This is A1. It will move like this. So this is how the superposition is working. Two pulses are coming. They are getting engaged with each other. The superposition is happening. After that, it is moving in their own paths. So it is moving itself. It is continuing its journey. There will not happen. There will no any other things will happen here. So that will remain the same. Okay. It is coming like here, superposition. After that, it is moving its own. Okay, right, own direction. It is moving. So this is the kind of superposition here. Sometimes that the negative of this one also happen, like this also happen. This is also superposition. We can say like this. There are two pulses. I am creating two pulses here. Creating two pulses here. Something like this. Okay. This is A1. Amplitude is A1. And this is A2 now. And this is A2 now. A2 now. So these twos are moving like this. What will happen? Superposition will happen. Yes. Superposition will happen. That will be looks like this. Can anyone tell me it is like upside or downside? The resultant will be upside or downside? The resultant will be looks like this or this. Upside or downside? Upside or? How it will be looks like? Right. It will be looks like this, guys. In the superposition situation, This will be looks like this. This will be looks like this. Let's say if this is A, the amplitude is A, so the resultant will be looks like this is A, no, this is upside down, right? This is like straight, so A1. So what will happen? This is the biggest one. When it's moving in this line, so these are going to merge. So this is the biggest one, this is the smallest one. They both are opposite. So what with the both phases are opposite, right? There is a phase difference between these two pulses. So what will happen here is, guys, the resultant will be A2 minus A1. The biggest one or the smallest one, so A2 minus A1. So this is the superposition. This is how the superposition will happen here. After that one, it will remain the same. After that, it will remain the same. It will remain the same. This is A2 and this is A1. After that one, it will remains the same. So this is A2 and this is A1. A1, okay? It will follow their own way, okay? Right. So this is known as the superposition. When it looks like this, can you write down the answer for this one? Can you write down the answer for this one, guys? Like, uh, this is the example number 1. This is example number 1. This is example number 2. I'm giving you another example here. Can you able to do this question? The third one, I'm giving like this. So these are algebraic sum of these two. So plus and the minus, you want to follow the plus and the minus here, guys. Okay, you want to follow the plus and the minus here, right? So look at this one. Let's say this is A1. Uh, this is A1, and this is A2. A2. You want to draw the superposition amplitude and after the superposition amplitude for this one, you want to draw the three of these image. Okay, right. So this is the first one. You should draw the second and the third one. Please write this one in your exercise book and give me the answer. So those who got the answer, please let me know you got the answer. Okay, right. Then I will explain this one for you. Do this one quickly. If you all completed the question, please let me know. Okay, right. So we will go for the answers now. You can go for the answers now. Okay, so, right. For this case, so we can go for the answers. Okay, so we know that, guys. So I can. Okay, right. So okay, students. So we'll move to this one. Okay, so look at this one. So in the superposition, this is A1 and this is A2. No, this is how it will be looks like. This is how it will be looks like. The amplitude of here is A is equal to A1 minus E2 here. A1 minus A2 here, because this is the greatest one, this is the lowest one. So this is the biggest one that is moving in the opposite phase here. This is the next one. So what will happen here is A1 minus A2. So this will be the resultant superposition. After this one, what will happen here is the waves will move like this. So this will move, the A2 will move in this direction because it will continue its own direction. This A1 will move in this direction. This is how it will happen. Okay, right. Now tell me, guys, did you all heard about the active noise cancellation? Did you all heard about the ANC in some of the headsets? Okay, right. In some of the headphones, you can see you can see the in the headphones, guys. Let's say this is the headphone. So this is how the headphones looks like. Okay, right. So in the headphones, you can see that logo ANC. ANC. In AirPods also, you can see the word ANC. What is ANC? ANC is, guys, active noise cancellation. Okay, active noise cancellation. So what is the meaning of that one? That's very simple. Okay, right. So look at this one. When you are hearing a music, when you are hearing a music through something or the speaker, through the speaker, what will happen? The wave, the sound wave, those will come from here. Okay, right. The sound wave will come from here, and that will vibrate the drums inside the ear. Okay, so you can using the vibration, you can hear the sound that is actually happening there. Okay, right. So when you are using normal headphones, okay, right. So when we are using normal headphones, what will happen here is, guys, what are they doing? They are just producing the sound wave to your ears. They are just producing the sound waves to your ears. So if I'm wearing a headphones, I can listen the sound clearly, but somehow I can feel the environment sound as well. That is not 100 percentage. We can't able to be like, we are unable to listen the surrounding sounds. We will listen at least like 5 to 10 percentage. We will listen the environmental sound while we are hearing the musics. Okay, right. So actually, what is active noise cancellation is, guys, that is very simple. There is a speaker here. This is the speaker inside the earphone. There will be a speaker, guys. There will be a speaker. This speaker, so let's say this is the earphone. Okay, right, this is the earphone. Inside the earphone there is a speaker here. So this is the speaker. This speaker will produce the sound. Here. Okay, right. And also what will happen here is, there will be some mic here outside. You can't see that one, that is inside the casing. There is a mic also here, guys. There is a mic also here. There will be some holes. Mic. What will happen here is, these mic will listen outside the surrounding. Okay, this mic will listen the surrounding sound. So it can able to catch the surrounding sound. So let's say it is catching the surrounding sound like this. I'm going to draw the surrounding sound pattern. This is the environmental sound. This is the environmental sound that is getting from the mic. Okay, what will happen here is, it will produce this mic, it will listen and it will produce the opposite of this sound. So that means what? That will be looks like this. The opposite of the sound, that will be looks like this. I'm going to draw that with white color. Like this. Okay, right, something like this. So what is actually happening here? Look at this one. This is the environment sound. This yellow color is the environment sound, and it is converting again from the mic using a special speaker. It is producing opposite of this sound, and this will reduce by another speaker here, or the same speaker. This will produce here. Okay, so what is actually happening here? There are two speakers. There's no two speakers. One speaker. It is pure. It is creating the pure music sound. So this is music sound. This is music sound. Okay, this is music, and this is the active noise cancellation. This is active noise cancellation. Okay, so this active noise cancellation, we are also hearing the environment sound. No, while hearing the environmental sound, at that instant of time, this speaker will reduce the opposite of that wave. So those two waves will what will happen? So those two waves becoming in superposition. So when those two waves will be superposition. What will happen? Those will cancel, and the resultant will be looks like this. The resultant wave will be looks like this. What is this? Silence. There's no way silence. So this is how the active noise cancellation inside the iPhone AirPods or Apple devices. If you are using the Apple devices, you can able to turn on the active noise cancellation. How it's working? From the outside mic, it is catching the environmental sound, and opposite to that sound it is creating at the same time. So we are hearing the environmental sound and the opposite sound, those will superposition, and we can get the silence here. This is how it's working. So without music, without playing any music, if I am wearing the headphones only, without playing any music, if I am wearing the headphones only, guys, what will happen? When you turn on the active noise cancellation, environmental sound and the opposite sound will go through the ears. So because of that one, what will happen? You can feel the silence. So if someone is talking with you, you can feel the silence. You can feel the silence. Okay, right. So this is how it's working. Some of the jammers also there, like Wi-Fi jammers and like signal jammers. These kind of jammers are working with this superposition principle. So when like when a mobile signal is coming through the antenna, when we create opposite of that wave using the jammers, what will happen at that area? The wave will superposition, and there is no wave, silent. So there is no wave will active. So if there is no wave there, no signal, no Wi-Fi, nothing is there. Okay, right. So these kind of works, so these kind of things are very important in physics. So you should know about these things as well. If you are interested, you can search active noise cancellation, and you can go for that one. Okay, further. Right. So I'm going to move to the next one. I'm going to move to the next one. Let's say, so in the, let's go to the next page. So look at this one, superpositioning two waves. So there are two waves are coming, guys. Two waves are coming, and they are meeting together. And this is the resultant. This is the resultant. After that, after the resultant, it will move. This will move in this direction. This will move in this direction. So this is how it will happen. Okay, for this one, look at this one. Look at this one. So when these are examples for the same amplitude waves. These amplitude and this amplitude are same now. So they are coming, they are opposite, the phases are opposite now. So when they are coming like this, so it will meet like this. This is the resultant, this is the superposition. So after the superposition, what will happen? The resultant will be zero, like a flat a line, a straight line, because this is plus A, this is minus A, plus A and the minus A 0. So this is the resultant, a straight line. A straight line. There is no any amplitudes here, because this is plus A, this is minus A. A minus B, A minus A is equal to 0. So this is the resultant. The resultant is like this. The resultant is here, the straight line, not the dotted line. Dotted lines are the waves, two waves. So this is the resultant. After that one, this will move in this direction, this will move in this direction. That is happening here. Okay, right. Look at this one. Look at this example. So there are different types of like, there are different shape of waves are moving, pulse are moving. These are not waves, these are pulse. These are not waves, these are pulse. So these kind of two different kind of pulse are moving together, and when they are coming together, what will happen here is for this one. So look at this one. Um, Okay, students, so look at this one. Look at this one, like there are two waves are coming, no? So these are the, like, this is the first wave, this wave, and this is the second wave. I'm using the two different colors. This is the second wave, no? Right. So if both of the wave will come together, the resultant will be looks like this. Look at this one now. The resultant will be looks like this. Looks like this. So in this case, what you want to do here is, guys, so this is the displacement of the red. This is the displacements of the red, okay? Displacements of the red. Sorry, amplitude of the rest of the red. This is the displacement of the blue. This is the displacement of the blue. I'm going to mark the red as well. This is the red. Okay, right. When you are adding together, look at this one, how we can add this one. I'm going to add these two. Look at this one now. Right. The blue one and the red one, let's say this is 5 centimeter plus 5 centimeter. Both are what? 10 centimeter line. This is the resultant. This is like, the blue one is like 4 centimeter. The normal one is like 3 centimeter. 4 plus 3 is 7. For an example, I'm telling you. Right. If this is 6 centimeter and 1 centimeter, this is 7. If this is like, this is 0, the red is no, there is no red here. If this is 5 centimeter, this is 5. So this is how the resultant looks like. This is how the resultant. So now the resultant is like this. So in this case, at this moment, what will happen? What you want to do here is, you want to add the amplitude of those two interacting pulses. Okay, you want to add the red and the blue. If the red displacement is like 6, blue is 3, 6 plus 3 is what? 9. So you want to draw the 9 line. That is the resultant. So this is how the resultant looks like. Okay, right. So this is how the resultant looks like here, guys. Looks like here. Okay, right. So when it's moving further, you can see the patterns. When it's moving further, yeah, look at this one. Okay, so when it's moving further, you can see the patterns, how the pattern is changing. So when it's moving further like this, in this direction, so this will be like this. Again, it is becoming like this. Again, it is becoming like this. After that, both of them are moving individually in these two directions. So this is how the superposition is working. Look at the pattern, how it looks like. So above diagram represent how wave pulse of different size coming from opposite direction with equal velocities getting superposition. Okay, right. So this is how it's working, guys. So look at the patterns. We are creating two pulses here, those two pulses are coming together and making the, let's say this is A1 and this is A2. Let's say this is A1 and A2. Both of them are adding together. A1 plus A2 is A. It is creating the wave here. After that, it is moving its own direction. Okay, right. So this is how it's working. This is how it's working. Okay, right. So yeah. Right, okay. So let's move to the next one after the superposition, right? So we can move over here, right? So this is how the superposition is working. And let's come to the here, the second one, obtaining displacement time graph by superposition of waves. Okay, right. So this is like one of the other use of this superposition. So this much of deep you don't need to go for, like these are very simple, like, so this is the displacement time graph is given here. So what you want to do here is obtaining the displacement time graph by the superposition of the wave. So you are going to obtain the superposition graph. Okay, right. So look at this one. Represented here is the displacement time graph of point A. Okay, right. So what I am going to do here is in this part, in this A. So when the two waves are coming like this, So in this one, this A, I'm going to draw the displacement time graph of point A when two identical wave coming from opposite side get superposition. Since two waves vibrate in the same phase, displacement of a wave A increases as they uh, superimpose. Okay, right. Here it is said point A act as an anti-node here. We will study about the nodes and the anti-node later. So it is now, it is like, now it's enough for you guys. Okay, right. This is the detail for the nodes and the anti-nodes. We'll study that one later. Okay, right. So this is the, that is little bit difficult. Okay, right. We are not going to go for that one right now. Right. Let's move to the interference. So interference is very easy. Interference is very easy. Look at this one. When there are two vibration, when there is a, in a ripple tank, we can place two spherical vibrators. We studied about the type of the vibrators in where, in the ripple tank. So those are, one is like a bar, the vibration, it will create the parallel wavefronts, and the spherical vibrators that will create the circular wavefronts, that will create the circular wavefront. So look at this one. So there are two vibrators are vibrating. So when they are vibrating, this will create one circular, this will create some circular wavefront, this will also create circular wavefront. When these two circular wavefront interfere, what will happen here is that will be looks like this, that will be looks like this. Okay, right. So look at this one, how the interference happening now. We can see how the interference is happening. Okay, right. So we can see the wave interference in this experiment. So these are the vibrators vibrating, two vibrators are there. So these are the vibrators are vibrating in the surface of the ripple tank. So this is how it will be looks like. This is a slow motion. So using your mobile phones, you can track these things now. Before that one, we used a different kind of instrument to slow down those things. So we'll study that one later. And so this is how the wave looks like. This is how the interference looks like. Look at this one. Look at these patterns. Using right. Okay, so he's like measuring the interference and other things here. So we'll move to this one. Look at this one, guys. This is how the interference looks like. There are two vibrators. These two are vibrators. This one and this one. These two are vibrators. These two are spherical vibrators. Those are vibrating together, and they are creating circular waves. They are creating what? Circular waves. When they are creating the circular waves, those two will interfere, and the pattern will be looks like this. Look at how it looks like. Okay, right. So we can experiment the interference as well in the ripple tank. So this is the setup of the ripple tank. Look at this one. This is how the ripple tank looks like. So he's right. This is the tank. This is the ripple tank. The bottom part is made by the glass. He's putting the stand here to keep the light here. This is the lamp. This is the light. These are the stands, and he's taking another vibrator. This is the parallel bar. Okay, this is the vibrator. This is the vibrator. It is having the motor as well with this with the attachment. This is the bar, straight bar, and there's a vibrating motor here. The flywheel of the vibrating motor is like that is different, so that will be quite different. So that is not a symmetrical, that is like a half circle. So the concept is like in the rotational motion part, I explained that with 25 theory students. Okay, right. We'll come to that one later. So vibrator. So in that vibrator, there are two attachment to the spherical vibrators. These two are spherical. So these two spherical vibrators is connected with the main vibrator. Okay, so we can, instead of using these two spherical vibrators, we can remove these spherical vibrators and we can only use this bar as well. Only use the bar also we can use the bar also, or else we can separate these two spherical vibrators and we can keep the small bar and it will vibrate. Okay, right. So he's pouring the water here now, and he is using the water level. He is making the table horizontal. Okay, right, making the table stable. This is the right. Look at this instrument. This is the instrument. We can change the frequency of the vibrator. Okay, we can change the frequency of the vibrator. That means how many oscillations I need to make within 1 second. Okay, so those things we can change using this frequency changing instrument. Look at the spherical vibrator. Look at the spherical shape vibrator. This is how it looks like. Okay, it is like some earbud, something like that. Okay, half of the earbud, but these are not earbuds. This is made out of plastic or steel. That can be varied. Okay, now the vibrator starts vibrating. So you can see how the waveform. Look at this one, guys. So like these are the vibrators, and this is like, actually these are the patterns we can see under the screen, so in the like ripple tank, there's a glass bottom is there. Under the glass bottom we will keep a screen or white paper. In that white screen we can see the reflections. You can see the reflections, you can see the shadow and the bright lines. So that one we are seeing now. Look at this one, how it's happening. Okay, right. While changing the vibration frequency, we can make different kind of patterns. So these are the circular waves. They are what? They are interfering together. So this one also interfering. These two are interfering. Okay, right. These two are what? Interfering. Look at this, students. Look at this one. So it creates a circular wavefront. This will also create a circular wavefront. In this case, what is happening? Superposition. This point, the superposition is happening here. Okay, so when we are making a wave and the other waves also coming together, at this point there is a superposition. Okay, there is a superposition. So we can see the higher amplitude there. There's certain amplitude, the higher amplitude there. Okay, right. And also, I can come to the next part as well. So this is how the patterns are working. So this one, look at this one. These lines are, in this line, all the two circular waves are superpositioning in this line. Look at the straight line. Look at the lines. So how the patterns looks like. Look at this is 3D. Look at these lines, guys. Look at these kinds. So these lines are like superpositioning line. These are superpositioning. Okay. Some of the lines are here. Like look at this one. This is like opposite to that one. Like this is like the positive one. This is like the positive one. And this one, look at these things, these ones. These are negative ones. And this is the positive. Both are superposition in the different direction. These are like superpositioning like this. I can draw that one as well. Look at this one, guys. You can say like this. Okay. So there are two vibrators, those are creating circular wavefronts. Look at this one. So I'm taking these two. I'm taking these twos. Okay. I need some more. I need some more, but let's create like this. Let's say something like this. The second one, I'm going to draw with a different color. Something like this. So look at this one. So what will happen here is, guys, what will happen here is, these are like, look at this line. It's hard to track the line here. Okay. Look at these lines. It should be here, but it's okay. So in a straight line, this one will be looks like superposition. This superposition is like there's a wave is coming like this, and the other wave is also, the other wave will be also like this. Other wave is also like this. Okay, right. So what is the resultant of these two? The resultant of these two will be looks like this, no? Like this. Let's assume one is coming like this, the other one is looks like this. What will be the looks like? Resultant will be 0. Okay, when those two superpositions, resultant will be 0. So you can see in this case, somehow this will also happen. One is coming, one wave is coming like this, the other will be looks like this. How will be the resultant? Will be the resultant looks like this. Looks like this. So you can see these three kind of superposition resultant wave. Okay, superposition resultant. One is like this, other one is like there is no wave, other one is looks like this, like this. So you can see these three lines. So one is like this one is flat, and then one is down. So look at this one. This 3D image. In this 3D image, you can clearly see this is like negative. This one is like positives. These are positives. These lines are negatives, and some of the lines will be flat. Some of them will be flat. Okay, right. So that is how the interference are working here. You can see the video. Okay, right. They are circling the positive interferences. They are circling the positive interferences. So they are drawing a line also here. They're drawing a line here. Okay, right. So so this is the clear experiment. The clear experiment is here, right? So you can see the dark and the white lines. You can see the dark and the white lines clearly here. In this case, I think they will put the lines, I think. Look at these lines. Look at these lines. So these are, some of them are Like look at this one, guys. So this is how the superpositions looks like. Okay, right. So they clearly mention here how it's working. Okay, right. So I think it's enough for you. It's enough for you now. So look at this one. So when two oscillating sources S1 and S2 with same displacement and same frequency oscillate inside a ripple tank, they produce vibrations in same phase. Okay, they will produce vibration in same phase. When considering the places where wavefront created by the vibrating sources intersect each other, amplitudes of these places get double as vibration get superposition. Okay, right. So in this case, these will be double up. These will be double up. These two will be can double up, double. So this is like the straight line. There's no intersections or superpositions. The resultant is flat. And here also double up, but in the opposite direction. But in the opposite direction. Okay, right. Okay, so vibration gets superposition. This is those places act as antinodes. Okay, right. Since harmonic motion increases further in these places, constructive interference are said to be occurring in these places. In figure below, a constructive interference is created at point P. Okay, right. At point P, there is a constructive interference. The constructive interference is happening. Okay, right. Right. Look at this one. The pattern obtained by the superposition of two or more waves is called an interference pattern. This phenomena is called interference. Okay, right. So this phenomena is known as interference. Look at this one. These white dots are antinodes, double crest and double trough, giving constructive interference. These are not crest trough causing destructive interference. So there are two kind of interference are there. There are two kind of interference are there, guys. Okay, right. One is constructive interference. The other one is destructive interference. Okay, right. This is known as guys constructive interference. These two are okay, right. Constructive. This is constructive interference. This is also constructive interference. Constructive interference. But this is destructive interference. You can see here. You can sorry. Destructive interference. Okay, right. Destructive interference. So these two are constructive interference. This is positive constructive interference. This is negative constructive interference because this is positive and this is positive. This is negative and this is negative. So this is all these two are constructive interference. But this is positive and this is negative. This is destructive interference, guys. So we can see constructive and destructive interference in the what interferences in the experiment we can clearly see. Okay, guys. So first of all, please draw this one in your exercise book and mark the constructive and the destructive interferences. Okay, right. Please mark the constructive and the destructive interference in your exercise book. Okay. Shall we move to the next one? If you're all done, please let me know, guys. You should know about the constructive interferences and the destructive interferences. So these are like very important part in your examinations. I think you all completed the. Okay, right. So this is how it's going to work. Right. Okay. So we'll go to the theory part now. We'll go to the theory part now. So in this case, constructive interference. So these are constructive interference. So I already told you that if the resultant displacement caused by the interference take the value higher than the displacement of each wave separately, then it's called the constructive interference. Okay, right. So in this case, what will happen here is the crest, both of the crest and the trough, they will interfere. So that will double. Okay, that will double. The amplitude will double. Okay, right. So I will told you that plus A in plus A, the resultant will be plus 2A, the amplitude. This destructive interference, like this is like this. Destructive interference means like, guys, look at this one. So like plus A in the minus A. So at that point, what will happen? Look at this one. Plus A in the minus A is interfering. That means plus amplitude in the minus amplitude. When we add both of these together, what will happen? The rest position will happen. Like there's no resultant. The resultant is zero. There's no wave there. Okay, right. So the rest position. Okay, right. So interference occurring in sound waves, and yeah, like in concert, in when there is a concert is happening, a musical concert or any other concert, so they will place the speakers, no, in our area, like they will just they will place the speakers. They are here, and they will place the in the classroom as well. They will keep the speakers in some of the places, right? Okay, but sound engineers, you already studied about heard about the sound engineers, those who are like, there are many sound engineers are there in the industry, in especially in music directions. Directors, they will hire good quality sound engineers, and they are dealing with the waves. They actually study about the waves and the sound wave and how they are working in the interference, refraction, everything they will study. The sound engineers, they will study. Okay, right. If I want to keep two speakers between some gaps, you should know about the lengths and how the wave will spread, and you want to know about the destructive and the constructive interferences. Okay, so those kind of things also there, right? Okay, using two speakers, I can cancel I can cancel the sound inside this area as well. So I already told you that active noise cancellation things. I already told you, right? Okay, look at this one. Look at this one. Figure represented two loudspeakers connected with the same frequency generator. Same frequency generator. Okay, right. Here, frequency and intensity of both emitted waves are same. Since they are connected to the same oscillator, emitted waves have the same phase. So they are same phase, like plus A in the plus A, minus A in the minus A, same phases. Okay, right. Since they are connected to the same oscillator, emitted waves have the same phase. If a person walking along the line PQ, if a person walking along this line PQ, he would hear sound with maximum loudness at point A, and hear no sound at the point, all at point represent at Sn. So here, guys, at this point, he will hear maximum. Constructive interference is happening here. Destructive interference is happening. Constructive, destructive, constructive, destructive, constructive. So this will happen. So when we are walking like in the line of PA, so PQ, line of PQ, what will happen here is there will be a fluctuation in the sound, like constructive, destructive, higher sound, lower, higher, lower, higher, low, that kind of things we can listen. Okay, right. So in concert hall also, the speaker should arrange in a proper manner to ensure that there will be no destructive interference. If a person is sitting here in this place, if the destructive interference is happening, what will happen here? He can't hear the sound. The sound will be low, actually. Okay, right. So these things will happen. So you should aware about these things. This is very important when there is a like sound. The sound engineering chapters, so these are very important. Okay, so in concert hall also, the seating also very important. Okay, the seeding, which seed is good. So those kind of things also there. Okay, right. So you should know about these things. Interesting things. Okay, polarization of waves. Right. Okay. So we are coming to the last part. We are coming to the last part now. Before the beat, yeah, we should complete this one. We are coming to the last part, guys. That is polarization of waves. Polarizations of waves. Okay, right. Look at this one. The direction of vibration responsible for the generation of a transverse wave exists perpendicular to the direction of the propagation of the wave. The occurrence of the vibrational direction of the transverse wave perpendicular to the direction of the propagation of the wave can occur in any direction in three-dimensional space in a manner as shown in the figure. Okay, look at this one. First of all, I'll explain you. Okay, right. The two arrows represent one on the plane corresponded to the direction in which it can vibrate. For example, we cannot specifically state the particle in the transverse wave created in a string move up and down perpendicular to the direction of the propagation of the wave only. The motion of those particles can occur from side to side or in the same plane within inclined at any angle to horizontal. Okay, right. So I'll explain you what is happening here. Okay, guys. So I'm going to explain this one using using light waves, because waves are like electromagnetic, mechanical. Two waves are there. Other classification is like transverse and the longitudinal. So I'm taking one transverse wave, light wave. I'm going to explain you the polarization. Okay, right. Look at this one. Okay, right. So look at this one. When I'm so before that one, I right. Okay, before that one, I'm going to explain you the theory a little bit. Okay, right. Look at this one, students. Let's say there is a light source is here. There is a light source. You should clear about this one. There is a light source. So light source means like from this point there are a lot of waves are coming. No, guys, there are a lot of light waves are coming. Like there's a source here. From this source only there's only not only one wave is coming. Also, like there are many waves are coming at this point. There are many waves are coming in this point. Okay, right. There are many waves are coming from the source. From the source. Okay, right. When I am like many waves. Okay, so this is the light source. Light source. So these lights are coming from all over, like the source is here. From this source, the light waves are coming in 360 direction. In each and every angle, the light wave is coming, like from, if this is a source like this, like this, like this. So in the all of this 360 degree, 360 degree, not only in one plane, it is coming like different planes. Like in this plane, there will be some waves. This plane, this, like this. So in this plane, there are lots of planes are there, right? So in many planes, many waves are coming from the source, like the sun, like the sun. What I'm going to do here is, look at this one, right? Look at this one. What I'm going to do here is, so in many places the waves are coming, no, right? Let's say one of the wave, let's say I'm taking only 1, 2, 3 waves here. I'm taking only 3 waves here. One wave is moving like this. One wave is moving like this. That wave is the straight line, the vertical line. Other wave is moving like this. Other wave is moving like this. So that is the horizontal one. Other wave is moving like this. Okay. This is the direction, the photons movement. Like this is how the wave is going to move. Now, like this. Okay, right. What about this one? Like this. So I'm taking 4. I'm taking 4 waves here. I'm taking 4 waves here. If I keep a slit like this, okay, if I keep a hole like this, a straight hole like this, what will happen? Only this wave will escape from this hole. Like this is the straight line, no? So this wave will only escape through that line. What about this wave? When it's going through the hole, it will it will hit the plane here. Okay, it won't go through that point because only this particle can move through the straight hole. Okay, right. Only this particle will move. Only when it's coming like this, only this wave will move in this direction. Okay, right. So these other 3 waves, those won't move. Okay, right. So look at this one. Look at the beauty. So in many planes, there are many waves are coming. So there are 4 waves are coming. In this case, when I'm keeping a hole like this, I'm getting only 1 wave here. I'm getting only 1 wave here. If I keep a hole like this, if I keep a hole something like this, like horizontal hole, what will happen? Our movement is like this, no? So if the hole is like this, what will do? It will stop. It will stop by this C. So it will stop by this C. So there will be no lights here. No lights here. Okay, right. So you should know about these things. First of all, I'm keeping 2 holes here. One is like these are unpolarized waves. So I'm keeping a horizontal hole here, vertical hole here. So the movement is like this. One wave is coming through this line. It can go through. But others, this one, other 3 waves can't move this hole because the motion is like this. So only this wave can move through this one. So it can move. If I keep the same one here, same hole here, from through that hole also, the particle will move. From that hole also, the particle will move. But when I change the direction of this one, what will happen? The particle is moving like this, no? Moving like this. But here, in this case, it will stop. Okay, so somehow you heard about polarized sunglasses. So in polarized sunglasses, when you are going outside, using the polarized sunglasses, actually what is happening here is you can see the sun. Without the sunglasses, you can't see the sun because it's too bright. You can't even see because lots of unpolarized waves are coming. When you are seeing through the hole like this, when you are like inside the lens, inside the sunglass lens, there will be small straight holes. So only the waves moving in this direction only coming, only this direction waves are coming, others are not coming, others are stopped by these lines, these holes. So we can't see that hole through our bare eyes, right? Using the naked eye, we can't see that one. Okay, so this is how we can stop many waves and we are allowing only few waves. So using that few waves, we can able to see the object without like too bright. Okay, we can see the light normally. So this is the concept of polarization. So we can only polarize. We can only polarize what kind of waves? Only transverse wave. We can't polarize the longitudinal waves, guys. This polarization is only for the transverse wave. We can't do this for the longitudinal wave, because longitudinal wave means sound wave. So when the sound wave is sound wave, the particle will be moves like this. No, when it's moving like this, so the polarization won't work. So it should be move like this, transverse wave. Okay, right. So this is very important here, and I can see you the I can show you the experiment for the polarization. Experiment for the polarization. Okay, right. So look at this one. So these are two polarized papers. Okay, right. These are two polarized papers. A single paper is a polarized paper. Normally this is too bright. No, this background is too bright. When I'm seeing through this only, seeing this with this polarized paper, this is like the brightness is low, because here lots of unpolarized waves are coming, but through this paper only few waves are coming. No, so that's why the brightness is low. There are only few waves are coming through the to our eye. The brightness reduced normal. Okay, right. The brightness, there's no that much of brightness, that will be normal. Okay, right. Here this is the brightness. You can see the difference between these two. This is normally we can see like normally using the naked eye, you can see here this is too brightness, this is dull. Okay, right, because through this paper this is polarized. This is polarized. Okay, this is polarized. Only there are nano, like we can't see the holes. Those holes are straight holes only. Through that straight holes only few waves are coming, which waves can move through the hole. Which wave can move through the hole. Okay, right. So I'm taking two papers, two polarized papers here, two polarized papers here. Okay, right. What I'm going to do here is look at this one. Okay, two papers are here. Look at this one. I'm taking two papers. This paper hole is straight like this. This hole is also like this. The second paper's hole also like this. I'm keeping like this, both. So through the hole, these kind of waves can accept. It will come, because those two holes are like straight. No, those two holes are straight. No, guys, like this. I'm keeping two polarized papers. Those holes are straight, so the waves can come. The waves can come here, but when you turn the next one opposite, like in 90-degree, the hole will change. No, right. When I'm turning this to 90-degree, you can't see anything. It's black. You can't see anything. It is totally black, because one is like in this direction, other is one is like this direction. So from the first one, when there are lots of unpolarized waves are coming through the first one, only these waves can go through this one. And when you turn this to 90-degree, this wave can also can't go. Okay, right. If I keep this one here, only this wave moving like this, only this wave. If I keep C here, what will happen here is only this wave can move through the hole. If I keep this here, only this way can move through the C, and after that, when I keep this B here, it will stop, because that is straight. No, it is moving like this. It is straight, so it can't. So this is polarization. Can you tell me if you understood or not polarization? Please drop me a message in the chat. Please drop me a chat. Please drop me a message whether you understood or not. Student, those who understood clearly, please drop me a message in the live chat. Please drop your message in the live chat quickly. Others, please drop me a message, guys. What about others? Each and every student, those who are watching the class, please drop me a message. Each and every students, those who are watching the class, please drop me a message. Don't be hesitate to drop me a message. Okay. Don't be hesitate to drop me a message. Only 2 of the students drop me a message. What about others? What about others? Very good. Okay, right. So this is polarization. Okay, right, students. So these are the important characters of the waves. These are the important characters of the waves like reflection, refraction, uh, diffraction, reflection, refraction, diffraction, and polarization, and the superposition. Okay, so these are the characteristics of the wave. Okay, right. So I hope you all understood this concept clearly. Guys. In the next class, we are going to study about the beats. Yeah, we are going to study about the beats. So beats are the very serious topic. Like you should understand. This is also very simple, guys. There's nothing to worry about these beats here. So beats, if you want to study the beats, like beat is only pending. Look at here. Only we should study about the beats. If you study the beats, that's enough. Our chapter is going to end, and we can do more questions. We can do the questions here. Okay, right. We can do the questions here. Right. Okay, students. So today we finished the main um, characteristics of the waves, and to next class we are going to move to the questions. So like there are several questions are there, guys. So you can from now you can do the questions like in this is the triple tank, or in triple tank also there are some lots of questions are there, guys. So you can start doing the questions from now onwards. Only beat is pending, so you can study the we can study the beat in the next class, and in the next class we will start the revision part in this 3.2 and 3.3. Okay, right. After finishing the 3.2 and 3.3, 3.3 is finished. Okay, right. After finishing this one, we are going to move to the 3.4 chapter. Okay, right. 3.4, that is also very important. But like that chapter from 3.4 and 3.5, we are getting so much of like practicals. Okay, so those are based on the practicals, and those are the things, guys. So okay, so in the next class we'll start the revision part. So I'm going to wind up the class now. So let's meet in our next class, guys. Physics is simple. Okay, right.